Have you ever wondered how you could, like, predict something that's unpredictable?
Hmm.
That's kind of what we're diving into today. It's a Monte Carlo simulation.
Yeah.
It's this method that uses randomness to solve problems
Interesting.
that would be, like, incredibly complex or even, like, impossible if you tried to tackle them directly.
Okay.
So it's kind of like finding order in all the chaos.
I like that, finding order in chaos.
And the name Monte Carlo itself is kind of a hint
Right.
at the element of chance involved, right? Because it's named after those famous casinos in Monaco,
Yeah.
known for their roulette wheels.
Uh-huh.
So are we saying we're, like, turning computers into high-tech roulette wheels to, like,
Yeah.
crack these tough problems?
You need to think of it that way. We're using random sampling, just like the spin of a roulette wheel,
Right.
to explore a huge number of possibilities and then arrive at a solution.
Wow.
And these applications are incredibly diverse,
Yeah.
from physics and engineering to finance and beyond.
Yeah, you sent over some really interesting research articles about how this is used.
Yeah.
And we'll be exploring examples from science and engineering today,
Okay.
starting with one that really caught my attention, Buffon's needle.
Okay.
Like, who would have thought that you could estimate the value of pi
Right.
just by dropping needles on a surface that has lines on it?
Yeah.
It sounds like a parlor trick.
It does. It's a classic example, though. And it goes all the way back to the 1700s. And it really illustrates how randomness can help us calculate a value that you would think is fixed.
Yeah.
Like the basic idea is to try to connect pi to things that we can measure, like
Yeah.
the length of the needles,
Okay.
the spacing of the lines, and then how many of the needles cross a line.
Okay, so let's try to paint a picture for our listener here.
Okay.
So we've got these needles.
Right.
And we've got this surface with lines on it, like a sheet of lined paper or something.
Huh.
What are the fixed values that we need to know beforehand?
So the length of the needles and then the distance between the lines.
Okay.
Those are predetermined. Those are our fixed points.
Got it. So where does randomness come in?
The random element is how each needle lands, like its position and the angle that it makes with the lines.
Okay.
So, imagine dropping these needles onto the surface,
Yeah.
and each one can land in a different spot
Uh-huh.
at a different angle.
Okay.
That's the randomness.
So it's like each needle drop is like a little tiny experiment.
Yeah.
And we're simulating this randomness over and over and over again.
Many, many times.
But how do we go from these random needle drops to, like, actually calculating pi?
So that's where the mathematical model comes in.
Okay.
There's a formula that connects pi to those measurements we talked about, the needle length, the line spacing, and the fraction of needles that cross the line.
Right.
And so by simulating the needle drops and plugging the results into that formula,
Okay.
we get an estimate for pi.
And I'm guessing the more needles we drop,
Yes.
the closer we get.
The more accurate our estimate gets.
Yeah.
Precisely.
Okay.
It's all about precision.
Uh-huh.
The more trials that you run, the closer you get to that actual value of pi.
Right.
And the more confident you are in your results.
Now, this is where it gets interesting.
Okay.
I read that some people actually carried out this experiment
Oh, yeah.
manually,
They did.
like with thousands of real needles.
You can imagine.
Talk about patience.
I know.
Like, wow.
But it highlights the historical appeal of this problem.
Yeah.
And it's a good reminder that even with computers,
Mm-hmm.
Monte Carlo simulation still requires us to carefully think about, how many trials are needed
Right.
for reliable results.
So speaking of those manual attempts, I did come across some historical crimes
Oh, really?
that seemed a bit too perfect.
Like what?
Like someone calculating pi to 7 decimal places using like a handful of needles.
Oh, wow.
Sounds a bit fishy, doesn't it?
There are some amusing anecdotes about people, perhaps, stopping the experiment as soon as they got an estimate close to the known value of pi.
Right.
Let's just say that not all historical attempts were as rigorous as they could have been.
So while Buffon's needle is a great way to illustrate the basic idea here,
Yeah.
it's not the most efficient way to calculate pi,
No.
but it does kind of lead us to a broader application.
Yes.
Which is using Monte Carlo simulations to find areas under curves.
Right.
And that's where things get really powerful.
Exactly. Think about a situation where you need to determine how a piece of metal cools down after it's heated.
Okay.
So the equation that describes that cooling process
Uh-huh.
involves an integral,
Right.
which represents the area under a curve.
Okay.
And sometimes that integral is impossible to solve using traditional math.
And that's where Monte Carlo steps in.
That's where it comes in.
It gives us a way to at least estimate the answer.
Yeah.
Even when we can't find an exact solution.
Precisely. One approach is called the hit or miss method. Imagine drawing a graph of the function you're trying to integrate.
Mm-hmm.
So you enclose that curve within a rectangle,
Right.
and then you scatter points randomly within that rectangle.
Okay, I'm seeing the connection to Buffon's needle here.
Yeah.
We're scattering points instead of needles.
You got it. And the fraction of points that fall under that curve is going to be proportional to the area under that curve.
Right.
And that gives us an approximation of the integral,
Wow.
and therefore a solution to our problem.
That's such a clever way to visualize it.
Yeah.
You're using randomness to solve a problem that you might not be able to solve directly.
Exactly.
Now, that's just one approach, though, right?
It is. Hit or miss is just one approach.
Okay.
We can also use what's called the sample mean method,
Okay.
which calculates the average value of the function in random points,
Okay.
and then multiplies that by the range over which you're integrating.
Okay, so we have two different ways to use Monte Carlo to tackle the same problem, but is one better than the other?
Well, they both converge to the correct answer
Okay.
as the number of trials increase.
Mm-hmm.
But the sample mean method tends to be more efficient.
So why even use hit or miss?
It really shines when we're dealing with more complex problems,
Okay.
particularly ones with many variables.
Mm-hmm.
So traditional integration techniques get really computationally expensive
Yeah.
as the number of variables increases. But Monte Carlo handles these higher dimensions
Wow.
much more efficiently. So it's built for complexity.
So it seems like as the problems get tougher, Monte Carlo simulation really becomes the MVP.
It does.
Okay, let's shift gears a bit here.
Okay.
And talk about something called thermal radiation view factors.
Okay.
What are those?
So imagine you have two surfaces that are radiating heat toward each other.
Okay.
The view factor tells us how much of the radiation leaving one surface actually reaches the other.
So it's like a measure of how visible each surface is to the other one
That's a great way to put it.
in terms of heat transfer.
Yeah. And view factors are crucial for understanding heat transfer in all sorts of applications,
Wow.
like designing satellites or power plants.
Mhm.
However, the mathematical formulas for calculating them
Yeah.
can be quite complex,
I bet I know what you're going to say next.
especially for complicated shapes.
Monte Carlo to the rescue.
You know, so we can picture this with like a really cool visualization.
Okay.
Imagine scattering points randomly on one surface,
Uh-huh.
with each point acting like a tiny source of radiation.
Right.
And then from each point, we shoot out rays in random directions.
I'm picturing like a disco ball,
I love that.
but instead of light beams, it's shooting out heat rays.
Exactly.
And then you count how many of those rays hit the other surface.
Right.
And the fraction that hit the target gives us an estimate of the view factor.
It's like playing a game of virtual darts,
Yeah.
where the darts are heat rays
Yeah.
and the target is the other surface.
And as with Buffon's needle, the more rays we simulate, the more accurate our estimate is going to be. But it's not just like randomly choosing any old numbers, is it?
No, it's not.
I noticed in the research that you sent that there's some nuance to how these random numbers are chosen,
Absolutely.
particularly for like the angles of the rays.
Yeah, you're absolutely right.
Yeah.
It's important to ensure that all possible directions for those rays
Mm-hmm.
are represented equally in our simulation.
Okay.
So to do this, we use weighted random numbers for the angles.
So it's not just blind randomness.
Right.
We have to be smart about how we use it
Yeah,
to make sure our simulation is actually accurate.
precisely. It all boils down to setting up the simulation
Uh-huh.
so that it properly mimics the physics of the problem.
Okay. I'm really starting to see the power and the versatility of this technique.
Yeah.
Now, how about we step things up another notch?
Okay.
I'm curious about how Monte Carlo is used in like bending beams.
So now we're entering the realm of structural engineering.
Okay.
So when you bend a curved beam, think of a curved piece of metal. The neutral axis, the part that doesn't experience any stress,
Uh-huh.
shifts away from the center line of that beam.
Before we go any further, can you help our listeners understand what we mean by neutral axis?
Sure.
Might be a new concept for some folks.
Of course. So
Wow.
picture a straight beam,
Okay.
like a piece of wood or something.
Uh-huh.
When you bend it, one side stretches
Right.
and the other side compresses,
Okay.
and right in the middle is a line that doesn't change length at all.
Okay.
And that's the neutral axis.
So in a straight beam, the neutral axis is right down the middle.
Uh-huh.
But what happens when the beam is curved?
In a curved beam, like the section of a hoop,
Yeah.
the neutral axis shifts inwards,
Okay.
away from the geometric center
Interesting.
of the beam's cross-section.
And this shift is what we're trying to calculate.
Yes.
Yeah.
It's called the neutral axis offset.
Okay.
And it's important for understanding the stresses and strains in curved beams. especially when designing structures.
Oh.
But calculating this offset with traditional math can be challenging,
Yeah.
especially for complex shapes.
I think I know where you're going with this.
Time for Monte Carlo to step in and save the day.
You got it.
So we can simulate this bending
Okay.
by randomly scattering points within the beam's cross-section and calculating the average distance of those points
Okay.
from the center of curvature.
Right.
But here's a catch.
Oh.
To get an accurate simulation, we can't just randomly choose points with uniform spacing.
Why is that? I would thought that randomly scattering points would give us a good representation.
That's a common misconception.
Okay.
Since we're dealing with a circular cross-section.
Right.
If you randomly choose points with uniform radii, you end up with more points near the center of the circle. So it's not really random.
So we'd end up with a biased representation.
Exactly.
Not a truly random one.
Yeah, to get a uniform distribution of points. We have to be more strategic. We select the radii from the square roots of uniformly distributed random numbers.
Okay, that's a little bit mind-bending.
It is.
But I'm following you. So we're essentially weighting those random numbers to make sure that the points are evenly spread out.
As I said.
And once we have a good distribution of points, we can use those to accurately calculate the offset.
Exactly.
All right, I'm ready for another challenge.
Okay.
How about we tackle torus segment volume?
Right.
First off, what exactly is a torus?
Think of a donut.
Okay.
That's a torus. It's a 3D shape formed by rotating a circle around an axis that's outside the circle.
So our challenge here is to find the volume of like a slice of this donut.
That's it.
Yeah.
We're specifically interested in a segment of the torus.
Okay.
Sometimes you can use an integral to calculate this volume directly.
Right.
But for more complex segments, that can be really difficult.
And this is where our trusty hit or miss method comes back into play.
You know, we enclose our torus segment within a larger shape.
Okay.
Like a rectangular box.
Okay.
Then randomly scatter points within that box and count how many fall inside the torus segment.
So it's like we're throwing darts at a box that has a donut in it.
Yeah.
And we want to see how many of those darts land in the donut.
Exactly. And the fraction of points landing inside the donut gives us an estimate of the volume of that torus segment compared to the volume of the box.
This hit or miss method seems so adaptable.
It is.
Like, could we use it for any shape as long as we can define whether or not a point is inside or outside the shape?
You're absolutely right. That's one of the biggest advantages of it. It's very flexible.
Okay.
And in some cases, it's the most straightforward way to tackle a problem.
Right.
When coming up with an explicit integral is just too complicated.
So we've gone from needles to cooling metal to heat rays to bending beams and now to donuts.
That's right.
What's next on our Monte Carlo adventure?
How about we explore something a little more penetrating?
Okay.
Let's delve into the world of radiation shielding.
Ooh, that sounds interesting.
Yeah.
Radiation shielding? It sounds kind of like something out of a sci-fi movie.
It might sound futuristic, but it's a very real and essential field. We're talking about protecting people and equipment from dangerous radiation like gamma rays.
Okay.
You know, think lead vests in X-ray rooms, or the shielding around nuclear reactors.
So it's all about creating barriers.
Right.
That either stop the radiation or at least reduce the amount that passes through.
Yeah.
But how does Monte Carlo's simulation help us with that?
Right.
It's not like we can build a virtual reality world and shoot gamma rays at virtual people.
That's where the power of simulation comes in.
Okay.
We can model the path of a gamma ray as it moves through some material, like a lead slab, for instance.
Okay.
And you can kind of picture it like this. Imagine the gamma ray is like a tiny bullet.
Okay.
Navigating an obstacle course inside the material.
And what are the obstacles in this obstacle course?
The obstacles are the atoms of the material itself.
Okay.
So when a gamma ray collides with an atom, it can either be absorbed, essentially stopping in its tracks,
right,
or it can be scattered in a different direction.
So it's like a game of chance for each gamma ray.
It is.
Will it make it through or will it get stopped?
Yeah, that's a great way to think about it.
Okay.
And we use random numbers to simulate these interactions.
Okay.
So we can determine how far a gamma ray travels before it has a collision. What type of collision occurs, whether it's absorption or scattering.
Right.
And if it's scattered, what direction it goes in.
So it's like a microscopic game of pinball.
That's a fun analogy.
With the gamma ray as the ball and the atoms as the bumpers.
I like it. And by simulating the paths of many, many gamma rays, we can get like a statistically accurate picture of how many will make it through the shielding material.
Now, I've read about something called a buildup factor.
Right.
What is that exact?
That's a really interesting concept. If gamma rays only traveled in straight lines, shielding would be relatively simple. We'd just calculate how much the radiation decreases as it passes through.
Right.
But it's not that simple.
Yeah, because the gamma rays don't just travel in a straight line.
Exactly. They're bouncing around.
Right. They're constantly bouncing off those atoms.
Exactly. And that's where the buildup factor comes in.
Okay.
It accounts for the fact that more gamma rays might emerge from the shielding than we would expect based on just a straight line calculation.
Because some of those scattered gamma rays can still find their way out.
Precisely.
So the buildup factor tells us how much more robust our shielding needs to be to account for all those bouncing events.
Exactly. And Monte Carlo simulation allows us to calculate that buildup factor and design shielding that provides the level of protection we need.
So we're using randomness to tame the unpredictability of radiation.
Yeah, that's a good way to put it.
We're taking something that's chaotic
Right.
and using it to design safer environments.
Exactly. And this idea of using Monte Carlo to analyze risk leads us to another fascinating application.
Okay.
Calculating the probability of failure for structures under stress.
Okay, now we're talking about like a bridge collapsing or a building buckling under pressure.
Yeah, things like that.
That sounds a little bit nerve-wracking.
It might sound scary, but these are really crucial considerations in engineering.
Right.
Let's take a simple cylinder.
Okay.
Like a thin-walled tube with a heavy weight on top of it.
Okay.
If the weight is heavy enough, the cylinder will buckle and collapse.
Right.
But here's the thing. The exact weight that causes that buckling isn't always so easy to predict. It depends on a number of things.
Okay.
Like the strength of the material, the thickness of the cylinder's wall, and even tiny imperfections in the material.
Oh, wow.
That might occur during manufacturing.
So it's not just how much force you apply. There's randomness inherent in the materials themselves.
Absolutely. And each of these factors has like a range of possible values.
Right.
So what we can do with Monte Carlo simulation is generate random values for each of those factors based on their statistical distributions.
So we're simulating thousands of slightly different cylinders.
You got it.
Each with its own unique combination of like strength and thickness and imperfections.
That's a great way to visualize it.
Okay.
And then for each simulated cylinder, we calculate whether or not it buckles under that load.
Right.
And by running this simulation many times, we can estimate the overall probability that a cylinder with those characteristics will fail.
So we're taking all of those uncertainties, those little imperfections.
All the variations.
And we're using that to calculate the overall risk.
Right.
That's got to be super useful for engineers.
It is. It allows them to make more informed decisions about the design.
Right.
And the safety factors that need to be built in.
But what if the simulations are super complex and we can't run enough trials to actually see any failures?
Right.
How do we get results then?
That's a great question. There are methods for dealing with those situations.
Okay.
One approach is called Wilks' method, which relies on order statistics.
Okay, I gotta admit, order statistics sounds kind of intimidating.
It's not as bad as it sounds.
Okay.
Imagine you run a limited number of simulations, let's say 50.
Okay.
And you rank the results based on how likely they are to fail. Even if none of those simulations resulted in an actual failure.
Yeah.
You can still make a statement about the likelihood of failure for the whole population.
Okay.
We do this by looking at the worst result you observed in your sample.
So we're looking at the most extreme case within that limited set of simulations.
Yeah.
And using that to make a broader statement about the risk.
Exactly. It allows us to draw inferences about the probability of failure.
Wow.
Even when we haven't actually observed any failures in our simulations.
That's pretty clever. But I imagine there must be some limitations to this approach.
Of course, the key is to have a large enough sample size to have some confidence in your conclusions.
Right.
And you also have to be aware that the worst case scenario in your sample might actually overestimate the real risk.
Right.
Which could lead to like overly cautious designs or even the rejection of a design that's actually perfectly safe.
So it's like a balancing act.
It is.
Between getting as much information as you can from a limited set of simulations.
Yeah.
But also avoiding being too pessimistic.
Exactly. It highlights how important it is to understand the assumptions and limitations of any statistical technique you use.
Okay, so we've talked about physical objects like beams and cylinders and stuff.
Right.
But can we use Monte Carlo for things that aren't physical objects?
Absolutely. We could use Monte Carlo simulations to analyze all sorts of systems.
Okay.
Including things like electrical circuits or even the way heat flows through material.
Now that's intriguing. I'm having a hard time picturing how you would simulate an electrical circuit.
So imagine a circuit with resistors and nodes, where the branches of the circuit connect.
Right.
We can use what are called random walks of virtual particles.
Virtual particles, are we talking about like tiny electrons zipping around?
Not quite. These virtual particles are more like a mathematical tool, not real electrons.
Okay.
We can think of them as taking random steps through the circuit.
Okay.
And the probability of them moving to a neighboring node is determined by the values of those resistors.
So it's like they're gambling as they move through the circuit.
Yeah, I like that analogy.
Placing bets on which path to take.
Exactly. And by simulating the paths of many of these particles, starting from a certain point, we can calculate the average voltage at that point.
So we're essentially creating a map of the electrical potential.
Yeah, a good way to think about it.
Within the circuit.
And this approach can be really useful for very complex circuits.
Yeah.
Where trying to solve the equations directly would just be a nightmare.
Now, how about heat flow? Can we use a similar approach for that?
Heat flow is governed by a law that's very similar to Ohm's law for electrical circuits.
Oh.
It's called Fourier's law of heat conduction.
Okay.
And that similarity means that we can use a very similar random walk technique to simulate how heat moves.
Can you walk me through how we would set up a simulation like that?
Sure. Let's say we have a heat exchanger plate.
Okay.
With a defect in it, like a small crack or something.
Okay.
And we want to understand how that crack affects the temperature across the plate.
Right.
So we would start by dividing the plate into a grid, just like with the electrical circuit.
Okay.
And we would use those virtual particles to represent units of heat.
So it's like we're mapping the heat flow onto a grid.
Exactly.
Then the particles are carrying the heat from one point to the next.
They move randomly from one node to the next on the grid.
Okay.
And the probability of them moving in a certain direction is determined by the thermal conductivity.
Right.
And the area of the material.
So if an area has a higher thermal conductivity, like a superhighway for the particles.
That's a great way to visualize it.
They're more likely to move through that area quickly. So that represents faster heat flow.
Exactly. And by simulating the paths of many of these particles, we can calculate the average temperature at each point on that grid.
Okay.
And that lets us see how that defect changes the temperature across the plate.
This is amazing. We're taking something that seems so chaotic, the way heat flows.
Yeah.
And we're using randomness to model it.
Right.
And understand it's like we're finding patterns in something that's unpredictable.
That's what makes Monte Carlo simulation so powerful.
Yeah.
Helps us deal with that complexity.
Right.
And gain insights into systems that would be so difficult to analyze otherwise.
All right, I'm ready for another mind-bending application of Monte Carlo.
Okay.
What else can we explore?
How about we step into the world of magnetism?
Okay.
Let's talk about magnetic phase transitions.
Ew, that sounds complicated.
And the Ising spin model.
Okay, I'm intrigued.
It's actually a very elegant model.
Okay.
That helps us understand how materials change between different magnetic states. Picture a lattice, like a grid.
Okay.
Where each point on that grid can have a spin.
Okay.
That's either up or down.
So it's like we've got a microscopic array of tiny magnets.
I love that analogy.
Each pointing either north or south.
Yeah. Now there's this kind of competition going on within the lattice.
Okay.
You've got thermal energy. That tends to randomize the spins.
Okay.
Making them point in random directions.
Right.
But then you also have what's called exchange energy.
Okay.
Which favors the alignment of neighboring spins they want to point in the same direction.
So at high temperatures, it's like chaos.
Yeah.
The spins are all over the place.
But
as we cool things down, they start to get organized.
Right.
And align with each other.
Precisely. And depending on the type of interaction between those spins, you can have different magnetic phases. For example, in ferromagnetism, all the spins want to align in the same direction.
Yeah.
Like a perfectly organized army.
Yeah.
But in antiferromagnetism, neighboring spins want to point in opposite directions.
Wow, that's so cool.
Yeah.
So how does Monte Carlo simulation fit into all of this?
We can use it to simulate this whole system.
Okay.
So we randomly flip spins on that lattice, and we calculate how that flip changes the overall energy of the system.
Okay.
We use something called the Metropolis algorithm.
Hold on a second. What's the Metropolis algorithm?
It's a way to decide whether to accept or reject changes in the system.
Okay.
So if a spin flip lowers the overall energy, we always accept it.
Okay.
But if it increases the energy, we only accept it with a probability that's determined by something called the Boltzmann factor.
Okay, I'm a little lost. What's the Boltzmann factor?
It essentially describes how likely a system is to be in a particular state
Okay.
based on its energy and the temperature.
Hmm.
So in our simulation, it helps us decide whether a spin flip that increases the energy
Yeah.
is likely to happen or not.
So if a spin tries to flip in a way that increases the energy, it's like rolling the dice, it might be allowed, but the odds are against it.
That's a great way to think about it.
Especially at lower temperatures.
Right. By repeatedly flipping those spins and calculating the energy changes,
Yeah.
we can simulate how that whole system evolves over time.
Wow.
We can actually watch as it transitions between those different magnetic phases.
So we're creating a microscopic movie of the spins
Exactly.
as they try to find their ideal arrangement.
That's a great way to visualize it.
And this simulation lets us calculate those important properties like the magnetization and susceptibility.
Precisely.
Okay, so this is all super cool, but are there any like real world applications for this?
Absolutely. Understanding these magnetic phase transitions is essential for developing new magnetic materials
Right.
that we can use in all sorts of technologies. Think about data storage devices, magnetic sensors.
Okay, you've convinced me Monte Carlo simulation is really powerful for understanding magnets.
It is.
What other adventures await us on this journey through randomness?
Let's enter the world of polymers.
Okay.
Think about those long, flexible chains of molecules like DNA or plastics.
Okay, I'm picturing a tangled mess of spaghetti.
A perfect image.
Okay.
Understanding how polymer chains behave
Yeah.
is crucial for so many different fields.
Okay.
It helps us design new materials, understand biological processes,
Wow.
and Monte Carlo simulation can help us visualize and analyze these complex systems.
So how do we simulate something as chaotic as like a tangled chain of molecules?
We can model a polymer chain as a series of connected units,
Okay.
each with a random orientation in space.
Okay.
So I imagine we're building a chain link by link,
Uh-huh.
with each link pointing in a random direction.
So we're creating a digital version of that spaghetti.
Exactly. But we can do more than just visualize the chain.
Okay, what else can we do?
The simulation allows us to calculate things,
Okay.
like the distribution of end-to-end distances, how stretched out the chain is on average.
Oh, wow. So we're going beyond just the visual.
Right.
We're actually like quantifying it.
Exactly. And to make it more realistic,
Uh-huh.
we can introduce constraints, like we can restrict the angles between links
Okay.
to mimic how real chains can't bend in any direction they want.
So we're adding a little bit of real world physics?
Precisely by comparing the results to experiments,
Yeah.
we can gain a much deeper understanding
Wow.
of how these chains behave.
Yeah, this whole discussion of polymers is making me wonder.
Yeah.
We've been talking about simulations that involve physical objects
Right.
or systems, but could we use Monte Carlo for more abstract things?
Absolutely.
Like, could we simulate a decision-making process or something like that?
You're thinking along the right lines. Monte Carlo simulation is used in fields like finance and economics
Oh, wow.
to model scenarios with a lot of uncertainty. For example, we can use it to make predictions about stock prices.
That seems like a whole other level of
It is, but the core principles are still there.
Right.
We use that random sampling to explore a range of possible outcomes
Yeah.
and estimate the likelihood of them happening.
It's incredible how versatile this technique is. It seems like there's no limit to what you can simulate.
The possibilities are huge and they're constantly expanding.
Wow.
As computing power grows,
Right.
we're going to see even more creative applications of Monte Carlo in the future.
Well, this deep dive has really opened my eyes to the power of Monte Carlo simulation. It's truly remarkable how we can use randomness to gain insights into so many different aspects of the world.
It's been a pleasure exploring these topics with you.
And to our listeners, we want to know what you think.
Yeah.
What are some scenarios where you think Monte Carlo simulation could be useful?
Right. What would you use it for?
How might you apply it to your own areas of interest? We'd love to hear your thoughts and ideas. Before we wrap things up, I'd love to touch on one more example that you mentioned earlier.
Oh.
You said something about using Monte Carlo to analyze that classic problem of distributing balls into bins.
It's a pretty simple problem on the surface,
Okay.
but it can lead to some really surprising insights.
Okay.
Imagine you have a certain number of balls,
Uh-huh.
and you randomly toss them into some bins.
Okay, I'm picturing like a classic probability puzzle here.
Right.
You're trying to figure out like what are the odds of certain outcomes?
Exactly.
Like how many balls will end up in this bin or that bin?
Yeah, and one question that we can explore with Monte Carlo is this. What's the probability that at least one bin is empty
Oh, okay.
after we've tossed all the balls?
So we're trying to calculate the odds that we end up with at least one lonely bin that has no balls in it.
Exactly. It seems like that probability would depend on how many balls and bins we have.
Right, of course.
And what's fascinating is that this problem connects to a very famous mathematical constant.
Oh, wow. Okay, what is it?
Euler's number.
Okay.
Often denoted as G.
I did not expect Euler's number to come up in a problem about balls and bins.
It's a surprise.
Yeah, how does that connection even work?
So as the number of balls and bins increases, the ratio of the total number of bins to the number of empty bins gets closer and closer to Euler's number.
That is wild. I never would have guessed that.
It's pretty cool.
There's this like hidden link between the simple probability puzzle and this fundamental mathematical constant.
It's a beautiful example of how these seemingly unrelated concepts can be connected in ways that you wouldn't expect.
Yeah.
And Monte Carlo simulation gives us a tool to explore these connections and test our intuition about probability.
It's like we're using randomness to uncover these hidden patterns and relationships that we wouldn't see otherwise.
It is.
I'm starting to understand why you're so enthusiastic about Monte Carlo simulation.
Yeah.
It really is incredibly powerful and versatile.
It's a technique that's applicable to so many different problems.
Right.
And it's a testament to the power of using randomness to understand and predict the world around us.
Well, this has been a truly mind-expanding deep dive into this world of Monte Carlo simulation. We've covered so much.
We have.
From simple area calculations to these complex simulations of systems and even these abstract mathematical concepts.
It's been a pleasure exploring these fascinating topics with you.
Likewise.
And I hope the listeners have enjoyed it too.
And to our listeners, we hope this deep dive has sparked your curiosity about the power of Monte Carlo simulation.
It's a technique that can be applied to such a variety of problems.
It really can.
From the everyday to the extraordinary.
And if there's one takeaway from all of this, it's that sometimes embracing randomness can lead us to the most elegant and insightful solutions.
I agree.
So until next time, keep exploring and keep asking those what-if questions.
That's what makes the world of science so fascinating.
Absolutely.